Thank you. Um, Next up, going to Aalto University, Rasmus Zetter.
Yes, hello, let me just start my video and share my screen. 1 second. There we go. Can you see my slides?
Yes, thank you.
Yep.
Great, thank you guys. Right, so hello everyone, I'm Rasmus Zetter from Aalto University. I'm a PhD student and I'm working in human neuroscience and MAG, so very much the same field as Niall who talked before me. My talk today won't be directly related to that, but rather to this open source software package that myself and some colleagues have released just recently. It's called bfieldtools very creatively, and it's a open source Python software for magnetic field modeling. And as I get started, I'll just kind of give the snapshot of it. So, well, we released it in May. We have if I say so myself, pretty nice website and a GitHub repo that you can take a look at. The website has some kind of code examples and kind of walk through way and so on. So the software package, it's centered around surface currents, and I would say applications are general purpose magnetic field modeling with surface currents, coil design in arbitrary geometries, again surface currents, modeling of magnetic shielding with some limitations, it's not COMSOL, and also modeling of eddy currents and transients. And finally, as a kind of bonus application, magnetic thermal noise computation as well. And we have 3 archive papers which kind of accompany this software. And from these first authors, you can see the 3 core developers of the software as well. So we have Antti Mäkinen, myself, Rasmus Zetter, and also Jonas Ivanainen, who are all from Aalto University. Right, so this is the snapshot, surface currents, those were the applications, check out the preprints. And then I'll go into kind of the topics of today. So when preparing these slides, I saw that Niall's presentation was before mine. So I'll just give a brief introduction to stream functions and how we handle them in bfieldtools specifically with our discretization. Then I'll continue with some, well, more or less notable features in bfieldtools, that some things that perhaps haven't been done this way before or I think are useful for coil design. Well, this includes how we handle boundary conditions, penetrations in the surfaces, for example, how we can use different basis function to make our problems really compact, how we use spherical harmonics to make our optimization problems even more compact, then how we actually optimize coils in the software package. Then I'll jump into manufacturing and how you actually go from having a bunch of windings to having a real life coil and an example. Of course, this won't be very exhaustive. We've seen quite a lot of different things today and how we can do things. If I have time, I'll show you the website briefly and then showcase some examples. And finally, I'll jump back to the software about issues, mailing lists, and if you want to contribute. Right, so I'll start with stream functions. So it's all about divergence-free currents on surfaces. So we have the surface current density J here. I think you can see my mouse, at least I've been able to see previous presenters' mice. The surface current density is as function of this stream function psi. It's a potential, scalar potential, but not the magnetic scalar potential. It's just a way to represent a surface current. And that is, the surface current is the gradient. First we have the gradient here on the surface and a cross product with the normal. So you rotate the gradient around 90 degrees to get the current. And this stream function psi, can be represented using any set of basis functions. So you have the actual basis functions themselves, h, and each basis function has a weight s. And specifically in bfieldtools, and in other previous publications as well, we use a triangle mesh discretization, since, well, triangle meshes are really adaptable. It's not confined to one specific geometry. And well, they're kind of ubiquitous. And yeah, so we use, in this triangle meshes, we use so-called hat functions as our basis. These are quite common in boundary element methods and finite element methods. If we were on 2D planes, these basic functions might be Fourier series, for example. Right, so hat function, there's one hat function for every vertex in your mesh, and they're defined as such that the hat function for this singular vertex is 1 at the vertex, and then the function linearly decays to 0 at the edges of neighboring triangles. So here's the hat function value in blue, the gradient of the hat function in red arrows, and then the black is the surface current density, so the rotated gradient, which then is a nice little current loop around that vertex. Then for when we have hat functions for every vertex on the mesh, we can represent any source-free current on that surface using this stream function weight vector S, which then has the length NV, or number of vertices. Right, so moving on from here, take a pretty big leap. I won't go too much into the physics or the calculations behind here, but based on this stream function vector S, we can compute most physical quantities related to the surface current using a simple linear mapping, using so-called coupling matrices. So just a linear mapping operator. For example, to get the magnetic field at some location, we compute this coupling matrix for the magnetic field and take dot product with the stream function vector. And then we have similar linear operators for magnetic vector and scalar potential, resistant matrix, calculus related things like the gradient, divergence, curl, Laplacian, and also the self inductance matrix and mutual inductance between two surfaces. And these we will use in coil design and just magnetic field modeling in general. So moving on to some notable features. So how we handle holes or enforce the boundary conditions in bfieldtools using this triangle discretization. So we want to have constant values on all boundaries, no current going in or out of the mesh. So the outer boundary of a mesh, that's easy to kind of numerically ground to 0, since the surface current density is defined by the gradient. You always have this constant value C, which is undefined, which is not nice to work in numerically. So it's just nice to ground the things. But for inner boundaries, inner holes, what we do is we combine all the hat functions, the basis functions of the vertices along the edges, into a single basis function that maps the same value to all of these vertices. And well, that's a pretty simple way to kind of enforce the boundary condition. So we get constant values along each hole. So in essence, we have 2 different hat function bases. We have the one I presented on the well previously, which has the length NV, number of vertices. Then we have a so-called inner hat function basis, which has the length and number of vertices minus the number of vertices on the boundaries, plus the number of holes, so inner vertices like the one here in green. So that essentially, well, per inner hole, you add 1 degree of freedom to the system. And as you can see in this example here, this whole value kind of floats. So you have in green current, and in red to blue stream function value, and it's well, it's kind of integrated nicely into the hole rather than being forced to go to 0 at the inner hole, which would not be very nice, because then you always have opposing currents around any inner or any hole, which well, it might work, but it won't give you nice solutions. Right, moving on to another set of basis functions, we have this so-called surface harmonics, which is a alternative basis for the stream function. And it's a spatial frequency series, and it's quite well known in geometry processing. And it's this thing on the right. So these are the first, let's see, 15 surface harmonic modes on the same mesh. So you see that it's increasing spatial frequencies as we go row by row. And each of these here is a solution to this eigenvalue equation where you have the Laplacian L, then we have the Vn, well, each of these is a V, the mode. You have a eigenvalue which describes the characteristic spatial frequency of the mode. Then you have a mass matrix of the mesh, and then Vn as well, again. And the hat function basis can be mapped to this surface harmonics or SUH basis using a linear mapping. So this large V is the matrix that's composed of all the different Vn's. And then A is simply another representation of the S vector. And the nice thing is that we typically work with low spatial frequencies, or we don't want jagged things. As such, we can truncate this series, and then A becomes quite a bit smaller. So, for example, we have a mesh with 10,000 vertices. We can, in an ideal case, perhaps only use 100 different surface harmonic modes to represent the currents we want, which makes optimization quite a bit faster. Right. Yeah. So, of course, this is on the surface harmonics modes are on triangle meshes. So, for example, you can see here this bunny. These are the 6 first modes on the, well, this is called Stanford bunny. It's, well, kind of this default mesh that people use. Then you can see also the same 6 first modes on a sphere and on a 2D basis, 2D sphere, sorry, 2D plane. Right. So, and these might look a bit familiar. So this surface harmonics basis, it is a generalized from, well, on a sphere it becomes the spherical harmonics, and on a 2D plane it becomes a Fourier series. And here you can see also the eigenvalues for the different meshes. So you see these 3 homogeneous components for the sphere, then 5 gradients, and then second order gradients, and so on. And you see these degenerate eigenvalues here. So the symmetry causes those. Well, for the bunny, there's no symmetry in the same sense. So the eigenvalues increase somewhat continuously. But right, yeah, you can truncate the series to limit yourself to limit the spatial how fast the surface current can vary on your mesh, and then also you can use it to just have a more compact representation of currents. And moving on, well, spherical harmonics are quite familiar to most of us, I think. So we just talked about the series representation of the surface current. Now a series representation of the magnetic field in free space. So again, we have uniform field, first order gradient, second order gradient, so on. And well, the spherical harmonic series is divided into 2 expansions, the inner expansion and outer expansion. If you look to the right, you can see the kind of inner expansion around the series origin, then a volume of where you have your currents, where the series won't converge. And then you have outer expansion, which goes to infinity, where again, the series can describe any magnetic field. And in bfieldtools, we can compute the series coefficients couplings directly from the stream function. So we have a coupling matrix for these. And that makes things quite a bit easier if you have, for example, a coil target region which is spherical, and you want a homogeneous field. So that's one specific spherical harmonics component. And then instead of having lots of target points in a spherical volume, you just have the up to L4 series of spherical harmonics coefficients that you optimize for. And well, we have different adjustable normalizations in bfieldtools, so you can adjust the radius of your expansion according to your needs. So, well, depending on what you want, how big the target region is. So these are kind of tools to make things easier in coil optimization. And that's what I'm kind of pivoting to right now. So how do we do that? So it's quite similar to what Niall showed. Very similar in fact. So we have the same bit different notation, but we want to determine a stream function vector S that fulfills some given requirements. For example, the magnetic field in some points, the spherical harmonics coefficients, or inductive coupling to another mesh, or so on. But that's not enough. That's an undetermined problem to just specify linear couplings. So we need to add a quadratic objective, make the problem convex, and then you can easily solve it. And well, typical kind of physical quadratic objectives that that people use are minimum inductance. So minimize the inductance of the surface current density while fulfilling some requirements, and also minimum power. So well, that's especially when we have larger currents, people tend to use that. And in bfieldtools, we can solve these optimization problems either using numerical iterative solvers or the standard least squares approach. And then the largest difference is that we can't use inequality constraints using least squares. Right, so looking at the right side now, the upper expression is what this kind of general standard formulation for quadratic programming problem. So this SPS here, that's the quadratic objective. If this P matrix is the inductance matrix of the mesh, then this is a minimum inductance optimization. If it's the resistant matrix, it's minimum power. And this QS we don't typically use, it's just as part of the standard formulation. And in these linear inequality and equality constraint parts, you simply plop in your requirements, for example, for the magnetic field and so on. I prefer using inequality constraints because then you can give a bit of slack to your problem. So instead of the solver trying to reach for or fulfill a specific equality constraint, you can say, okay, try for, it has to be within 1% of this, or within 5%, depending on what you want. Right, then looking at the second expression here on bottom, this is very similar. This is what you would look at in a least squares or regularized least squares approach. So we have the same quadratic objective. We have a trade-off parameter lambda, which, well, trade-off between getting smallest quadratic objective function value and then your actual requirements. And actually, this can be formulated as the first line in the upper expression as well. I'll talk a bit more about the use of iterative solvers in bfieldtools, since that's what I mostly use. So we use this CVX-Pi framework, convex optimization in Python framework. So we can use lots of different solver backends. There's different commercial solvers, some open source solvers, very general use. I found that some of the commercial ones are more robust, especially in larger problems, which brings me then to that it's good to try to keep problems compact, just generally, and the spherical harmonics and surface harmonics are kind of tools to help us with that. So for example, in a good case, if we have 6,000 vertices and 1,000 target points in which we want to specify the magnetic field, we can perhaps boil that down to 100 surface harmonics components and 24 spherical harmonics components. So that brings the computation down from tens of seconds to 100 seconds, let's say, on a typical desktop computer, to a couple of milliseconds, which then makes iteration quite nice. Of course, when using surface harmonics, we need to solve the eigenvalue equation first, but that's a one-time cost, and that's not at all on the same order of time scale. On the right side here, I just show a small snippet, a demo of how things look in the bfieldtools code. So if we want to optimize a coil, we first give it some specs. This is a Python dictionary. Okay, we have a coupling, which is here the B field coupling at some target points, and this is an inequality constraint. So we give the absolute error that what we allow, and then the actual target that we go for. So then it's target field plus minus 0.01. Then we have a second specification or constraint here for the stray field or fringe field at some stray points, the same error requirements, and now we aim for 0. So, and then we call this optimization function. We give it this coil object which holds the mesh and all the inductance matrix and lots of handling things. We give it a list of specifications. Which objective do we want to use? In this case, just specify a string, the minimum power, and say which solver we want to use. And this then returns the optimized S vector. Right, so just taking a step back, we have the S vector. It might look like this, for example. We want to make this into windings. Well, that was covered quite nicely already. So we, well, you can, if you quantize it a bit, you start to see where this is going, making it windings by isolines on the stream function. And of course, you can choose the number of isolines freely. More isolines or contours results in a better approximation of the continuous surface current density. But at some point, they might come so close to each other that manufacturing is tedious or impossible. Right, so that's a trade-off there. So taking a step back, the workflow that we have is that we first specify a geometry, in this case a mesh. Where are the windings allowed to go, or the surface current? We define a specification of, for example, the field at any number of points. Here on this image we have a target region in green behind the mesh, and then some stray points in red. We set the optimization target, the quadratic objective. We solve for the S vector, either using least squares or iterative solver. And then we convert the continuous current density you get into discrete current loops. And now we have these floating loops that don't have any feed current. And getting from here to an actual coil that you hold in your hand is not trivial at all, as many of you know. Right, so you need to connect all these windings in series without affecting the coil performance too much. This is not at all trivial. It will be highly dependent on your manufacturing method, the physical scale, the current amplitudes, and all kind of these things. And we've seen lots of examples of these today with machining and 3D printing PCBs. And well, here I just have some examples, and I don't think I need, well, all of these have been covered except MEMS, I guess. Well, that's really small scale stuff then. For coil formers, I guess either machined or 3D printed. I think there was a question in chat about, well, how do you 3D print? That's a very wide field. So that's, I guess, will require iteration and depend on the application and scale and so on. I preferred sintered laser things. Just to show an example myself of how to do things or realize manufacture a coil based on this design, a bit different. So I'll show you here. So of course this is a PCB, so it's kind of the easiest case possible, or it's planar. It's a 3-axis homogeneous field control system using 2 planes which have holes. These holes were required. So we couldn't just, required to be in their specific locations. We couldn't just put them where the windings weren't. So the coils were kind of retrofitted in that sense. And here on this lower row, you can see the XYZ coils that we then got through the optimization. And you can also see the target region, which is a sphere there in the center. And from the scale, you can see there's approximately 1% error from within these, within the target region, even though we have this large hole in the lower PCB. Right, so this is what we ended up with. This is from the PCB CAD software. As you can see, it's a bit of difference. It's now a multi-layer PCB, which has XYZ in the same structure at different layers. And if we zoom in at a specific point, for example, following this purple line, you can see that it jumps in, kind of spirals inwards, and it changes direction here, and always going around. And when we get in the center, we have a via, one layer down, and this green layer finishes the loops and traces back to cancel as much of the stray field as possible. And the same is true then for the yellow-red layer pair here. Right, so that's how we did that. And this is unfortunately quite a bit of manual work, not as much as winding the coils yourself, but still. And here you can see the finished product, which performed quite well. Right, so at this point,
Sorry, what's the length scale on this photograph?
So let's see if I remember correctly. It's 3.5 by 3.5 centimeters. So this is small, but not like ridiculously small, but somewhat small. Yeah, and I think I have time to show the website just quickly. So here we have it. And on the website, if you want to take a look, we have, well, just kind of a general README with features, dependencies, license, so on. Installation instructions, some background literature, but the thing I like the most is we have these examples with coil design, applications, how to reproduce the examples in our papers, some about thermal noise, and validation computations as well, just to see that everything works. And if I just click on something, here we have an example of modeling magnetic shield. Just setting up geometry, this is all commented, so on. A biplanar coil within a cylindrical perfect linear magnetic shield. And we just show how we can take the distortion from the magnetic shield into account, since the coils are very close to the end, so there's quite a bit of distortion due to the shield. So how it would be in air, so to say, and how, if we want to make a homogeneous field with the coil that position within the shield, then we get coils like this instead. Yeah, and all kinds of different examples here. Yes. Going back to the actual presentation, let's see if it jumps to the beginning. Yes, it does. Sorry about that. Yes, so we don't have a mailing list yet for the software project, but GitHub is up and running. So if you try the software, have any bugs and other issues or questions, GitHub works great for that. You can also send me or any of the other authors an email to ask questions or for help or anything like that. If you have ideas for new functionality or like to contribute in some way, I'd love to hear some ideas. And I myself or some other of the authors can or developers can help you get started with things, and then we can hopefully kind of end up on a pull request that can be integrated into software. So with this, I'd like to thank you for your time and hope you have any questions.
I have a question that's unrelated to your talk, but I just briefly saw on the website that one of your examples is conformal mapping. So what kind of conformal are you using? Are you using like a RISI flow or?
So that's a very good question. So because this is my colleague's work, so I actually can't answer this.
Oh, okay. I was just curious. It's not really.
Yeah.
Okay, sorry.
Well, here we have, based on these course notes, section 7.4. So angle preserving conformal mapping. I don't know. Good question.
Great, thank you.